So, hello friends, welcome to a lecture series on nonlinear programming. So, now we come to search techniques. You see there are some nonlinear problems. There is no unique method to solve any nonlinear problems, nonlinear programming problems. However, we have studied some problems, some specific problems which we can solve using KKT conditions or quadratic programming or separable technique or geometric programming. Okay. But all the problems cannot be solved using these techniques, there is no any unique method. So, we go to numerical approach or search techniques, okay, to find at least approximate solution, optimal solution of a given nonlinear problem. So, if we first start with unconstrained optimization problems. We have already discussed that a problem with without any constraint, that is simply minimization of a function f x, x belongs to R n, such problems are called unconstrained optimization problems. Now, the question arises, how can we find out a point, say x bar belongs to R n, which solves or at least approximately solves the given problem P, okay? Because in general our analytical techniques may not work for all type of optimization problems. So, we move to such techniques. So, this is the reason that we should move to such techniques, because all the kind of optimization problems cannot be solved using analytical approach. Now, what is the basic scheme? The common basic scheme is of the form xk plus 1. It is a recursion algorithm basically, all the search techniques are recursion algorithms. So, the basic scheme is you take xk plus 1, that is the iteration at k plus 1th point, is equals to xk, that is the previous iteration, plus alpha k dk. Now, xk is the current solution, okay. Dk is the direction of movement from xk. You see that you are moving from a point xk to xk plus 1, you have two distinct points xk and xk plus 1. How to move from xk to xk plus 1? So that we are moving towards the optimal solution. If it is a minimization problem, then we are moving towards the minimum point. How can we find a direction in which we should move? So, that is dk. And next is alpha k, which is greater than 0 and is called a step size. The step size is the distance up to which we move from xk in the direction of xk, that is how much direction from how much distance from xk we should move so that we can find the improved solution, okay. So, this is a basic scheme. So, basic scheme what we have to find, basically we have to find two things. Xk is the current solution, it is this is given to us or we can find. Next is alpha k is the step size which we have to find, and dk is the direction in which we should move so that we can get the improved solution in the next iteration. So, two things we have to find in all the schemes, alpha k and dk. So, how to find alpha k and dk? To find the next iteration xk plus 1 such that we move to the solution of P in the efficient manner, okay. So, that is the main problem. Now, next is descent property. What is descent property? An algorithm for solving P, you see. This is the problem P, that is minimization of f x subject to x belongs to R n. This is a minimization unconstrained optimization problem. Now, when we say that it satisfies a descent property means you see you start from a point current solution is xk and finding alpha k and dk, you comes to alpha xk plus 1, that is iteration at k plus 1th point, okay. So, xk plus 1 will be better solution than xk only if the function value at xk plus 1 will be lesser than what we obtain at xk. Okay. So, then we say that that satisfy that it satisfies descent property, because the functional value C, functional value at xk plus 1 is less than fxk, that is we are moving towards the improved solution. In the case of minimization, we are moving towards the improved point where the value of f are improving or decreasing. Okay. So, then we say that it has satisfied descent property. Okay. Now, order of convergence. Now, we have different such techniques to find out an optimal solution of a given problem P. Which scheme is better? Okay. So, that will be decided by its order of convergence. And what is order of convergence? Let us see. Let us sequence xk. You see, when you start from an initial guess, say x naught, using any scheme, then you come to x1, then x2, then x3 and so on, xk plus 1 and so on. Okay. So, you have a sequence of xk, x naught, x1, x2, x3 and so on, you have a sequence. And suppose sequence converges to a point x bar, suppose xk will tends to x bar. Okay. And let xk is not equal to x bar for sufficiently large value of k, let us suppose. Then the quantity this, of course, if you take the distance of xk, the point obtained at the kth iteration, the difference of the point obtained at the kth iteration with x bar, that will be the error point, that will be error at the kth iteration. Okay. This is simply give the error term at the kth iteration. Now, suppose there exists p and alpha greater than 0 such that norm of xk plus 1, that is whatever we obtain at k plus 1th point minus x bar upon xk minus x bar whole power p as k tend to infinity tending to alpha. So, then we say that the order of convergence of the sequence is p. If this expression is tending to alpha as k tending to infinity, then we say that the order of convergence of the given scheme is p. Okay. You can simply understand that this norm as a distance of xk plus 1 with x bar, distance of xk with x bar. Okay. Now, if p is equal to 1, okay, then we say that the convergence, that the sequence converges linearly. If the p equal to 2, then we say that the sequence xk converges quadratically, or it is having quadratic convergence. That means, if we have a larger value of p, the order of then the convergence rate will be faster. More the value of p, more faster will be the scheme. So, we are always in search of those schemes, those techniques which is having larger order of convergence. Now, next is unimodal function. So, these are the basic terminologies we should know before starting any such technique. What is the descent property? What is the order of convergence? Okay. And what is unimodal function? We should know, then we should go to such techniques. Okay. Now, unimodal function. What is unimodal function? Now, suppose a function f which is defined from an interval a comma b, closed interval a comma b to r, and it is said to be a unimodal function if it has only one peak. You see, in a to b, if in the interval a to b, suppose this is interval a comma b, if in this interval the function has only one peak, here one peak, only one minimum, either minimum or maximum. Peak means either minimum or maximum. If it is only one minima or one maxima in the entire interval a to b, then we say that the function is an unimodal function. Okay. Function may be like this also, function may be like this also in a to b. Okay. It is only one peak. Okay. So, such functions are called unimodal function. Now, here we are considering minimum objective function, matlab I mean optimization problem of minimization type, and similarly we can derive the expressions for optimization problems of maximization types. So, we are dealing with minimization over here. Now, consider a unimodal minimum function. Minimum function means objective function is of minimization type. That means the peak in the objective function is of minimum type, of this type of problem we are considering. Okay. So, if it is minimum type problem, some alpha is there in between A and B such that it has only one peak. That means if it has only one peak, I mean only one minimum in the interval A to B, that means before this alpha it must decrease, and after this alpha up to B it must increase, if it is a unimodal function, because according to definition unimodal function it must have only one peak, I mean only one minima in between A and B. That means if the point of minima is alpha, that means f is decreasing, in A to alpha, and f is increasing in alpha to B. So, that is the main concept of unimodal function. If it is unimodal maximum function, then if it is unimodal maximum function and it suppose maxima is obtained at beta, then it first increase and then decrease. It increases up to beta, and after beta up to B it decreases. Okay. In unimodal minimum function, suppose we are having this type of problem. Okay, any problem, this type of problem suppose we are having. Minima, for minima, we are not discussing about the continuity or differentiability of the function. Okay, function may or may not be continuous or may not be differentiable. We are only thinking that function is a unimodal function, that is it has only one minimum point in A to B. Suppose it is A, and it is B. It is a minimum point. Okay. It first decreases and then increases. Okay. Now, the first interval A B, is called first interval of uncertainty. What is our aim? Our aim is to find out the minimum point of the given problem P. We have some given problem P, some given f x which we have to minimize subject to x belongs to R n. Our aim is to find out the minimum value of the objective function f x. Okay. Now, for that we are always try to reduce this interval. Okay, this is the first interval. Okay, we are always try to find out some experiments in this interval such that the minimum point always lies in between that interval, lies in the interior of that interval, and we are always try to reduce the size of the interval, width of the interval, and such intervals are called interval of uncertainty. Okay. In every like iterations, we are trying to find out a new interval of uncertainty such that the interval of width of the interval of uncertainty becomes smaller and smaller. Okay. So, and in each interval of uncertainty minimum point will lie. Okay. Now, suppose in any scheme you find out two experiments. Two experiment means two iterations. You perform two iterations. Okay. You find out two iterations. Suppose you find out first iteration over here x1, and next iteration you find out here suppose it is x2. Okay. You perform any such technique which we discuss afterwards. You find two experiments. Suppose experiments are x1 and x2. Okay. It may be possible in this case fx1 is less than fx2. Okay. In this case fx1 is less than fx2. Now fx1 is less than fx2. So minimum will belongs to x minimum or minimum point, which is this point, will belongs to which interval? Will belongs to a to x2. Why a to x2? Why not x1 to x2? Because this x1 may be here also, because here also fx1 is less than fx2. If we say in between x1 and x2, then here x1 to x2 does not contain the point of minima. However, a to x2 always cover the point of minima, because we are choosing x1 less than x2. We are taking two experiments such that x1 less than x2. Okay. If x1 is less than x2 and value of function fx1 is less than functional value of fx2, so of course minimum will lie in between a to x2. Now suppose fx1 is bigger than fx2. Suppose this is the case. Suppose x1 is here. Okay. Suppose x1 is here. If x1 is here, so this implies minimum will belongs to which point? Which interval? x1 to b, because minimum is here. Okay. Because minimum is here. Again you may say that the minimum should lie from x1 to x2, but it is not true. x2 may be here also. If x2 is here, because x1 is less than x2 and if x1 is greater than fx2 holds here also, and if it is here and you are saying that minimum lies between x1 and x2, which is not true, because minimum is here. I mean, x2 and x1 are the arbitrary experiments which we are performing. Okay. So we do not know where minimum is. But minimum always lies in this interval, and if fx1 is equal to fx2, if it is equal, suppose here, so in this case minimum will lying belongs to x1 x2. So from any scheme, from any basic scheme, from any such technique, we first find two experiments, okay, x1 and x2. We find the next interval of uncertainty, which may be this or this. This case rarely happens because fx1, most of the cases rarely happens that fx1 is equal to fx2. So in most of the cases we are having either this case or this case. So next interval of uncertainty will be either this or this. So definitely the width of this interval will be x2 minus a, and the width of this interval is b minus x1, which is less than b minus a. So in each step, in each iteration, we are trying to find out the next interval of uncertainty such that the minimum point will lying in that interval, and we are making interval smaller and smaller. So that is a basic scheme, that is a basic property which we are using in this any such technique. Okay. Now next is measure of effectiveness. What it is? It is denoted by alpha and it is defined as ln upon L naught. Ln is simply width of the interval of uncertainty after n experiments. Suppose you perform n number of experiments. So ln we are defined as width of interval of uncertainty after n experiments, and L naught is the initial width of uncertainty. Initial width means b minus a over here. So definitely alpha will be less than equal to 1, because in each iteration we are trying to reduce the size of the width of the interval. So ln will be definitely less than or equals to L naught. So ln upon L naught will definitely be less than or equals to 1. So smaller the value of alpha, that means that means we are making the interval uncertainty smaller and smaller. Okay. Now, the first search technique is dichotomous search technique. Now, what it is, let us discuss. The first search technique is dichotomous search technique. You see, you have to experiment. You have the initial interval is given to you. Initial interval is given to you. Interval is a comma b, closed interval a comma b. You have to find out experiments and the next interval of uncertainty. Okay. How to find that? So, in this search technique, in this scheme, what we do, we basically, so this is L naught. We first define L naught. L naught is b minus a, the initial length of uncertainty, that is b minus a. Okay. Now, you find two experiments here, x1 and x2, such that x1 and x2 are, suppose, delta distance apart. Now, we take the 2 point at a equal distance from the midpoint of this, that is so this is L naught by 2, this length is L naught by 2, and we are making it delta by 2. We are shifting 1 point delta by 2 on the left side of the interval, and we are making 1 point delta by 2 on the right side of this interval. This is delta by 2 and this is delta by 2. So, x1 will be equals to a plus, you see, the left point a plus, this is L naught minus delta by 2. This is from here to here, it is L naught by 2, and L naught by 2 minus delta by 2 plus a will give this point x1. If you add L naught minus delta by 2 on this a, we will get x1. Okay. And how to find the next experiment x2? X2 is L naught by 2 plus delta by 2. So, a plus L naught plus delta by 2, that will give x2. So, this is how, this is how we can find x1 and x2. In this PPT, we have denoted a by xl, that is a left point, and this by xr. Okay. So, we are placing two experiments such that the experiments are lying delta by 2 on the left side of this line and delta by 2 on the right side of this line, okay, such that. So, next we find out the sign fx1, we find fx1 less than fx2 or fx1 greater than fx2. Okay. Next we find out whether fx1 is less than fx2 or fx1 is greater than fx2. If fx1 is less than fx2, this means minimum will belongs to, because fx1 is less than fx2, this means minimum will belongs to xl to x2, and if this is the case, then this means minimum will belongs to x1 to, minimum will belongs to x1 to xr. Okay. Now, this will be our next interval of uncertainty. If suppose this is our next interval of uncertainty, so this will be xl and this will be nu xr. Again we divide, we take the midpoint and place the next two experiments, delta by 2 on the left side and delta by 2 on the right side. Okay, suppose this will be our next experiment. So, next experiment will be now xl to x2. Again this length is suppose L2, which is x2 minus xl. Okay. Now we again take the midpoint of this, place one point delta by 2 on the left side of this, which is x3, and one point here which is x4 delta by 2 on the right side. So what will be x3 now? x3 will be xl plus L2 minus delta upon 2, and x4 will be xl plus L2 plus delta by 2. Again we will check the sign of fx3 and fx4, whether fx3 is less than fx4, fx3 is greater than fx4. On the basis of this we can decide the next interval of uncertainty. Okay. So this is the main scheme. We place the two experiments starting from midpoint, delta by 2 on the left side and delta by 2 on the right side. So if you find the next length L2, L2 is x2 minus xl. x2 is what? x2 is this value, that is a plus a or xl, a means xl, okay, that is xl plus L naught plus delta by 2 minus xl. So it is L naught plus delta upon 2. This is L2. And from here also if you find L2, it is same because distance are same, it is xr minus x1. What is xr? xr is L naught plus xl, and xl is x1 is this quantity, a is xl, so it is minus xl and minus L naught minus delta upon 2, which is equals to xl cancel out, it is delta. So both are same. Okay, whether we have this next interval of uncertainty or this, it will remain same. Okay. So what we have obtained, now the number of experiments n are always even, because here in each iteration we are calculating two experiments, x1, x2, x3, x4 and so on. So number of experiments either 2, 4, 6 and so on. Okay. Now the interval of uncertainty ln, I mean width of interval of uncertainty will be, if we perform two experiments. So we have seen that interval of uncertainty is that we have seen L naught plus delta by 2. Okay. Basically what we are doing, we are taking the half of the length. Here what we are doing, we are taking the half of the length L naught by 2 plus delta by 2, L naught by 2 plus delta by 2. In the next experiments x3 and x4, if you find the length of interval of uncertainty or width of interval of uncertainty, that will be simply half of this, because now the next length is this. If you take the next length as L naught in the initial interval, so it is L naught by 2 plus delta by 2. Now now in the next iteration, now length is this this quantity, so this by 2 plus delta by 2 will be the next length of uncertainty, that you can easily show also, you can easily see also. Okay. Now in the sixth experiment, this will be half of this plus delta by 2 and so on, because in each step we are making L naught by 2 plus delta by 2. Now this is the next interval length, so this by 2 plus delta by 2. Now this is next length, this by 2 plus delta by 2. So what happens after say 2k number of iterations? After 2k number of iterations, say n equal to 2k. If n equal to 2k, so it is, you see, it is 1 by 2 whole cube, Okay. So, it is L naught upon 2 raised to power k. It is 2 into 3. So, it is 2 cube. If it is 2 into k, so it is 2 k plus delta, it is 2 raised to power k plus delta 2 raised to power k minus 1 and so on plus delta raised upon 2. If it is 6, so delta, it is delta upon 2 cube plus delta upon 2 square plus delta upon 2. If it is 2 into k, so it is delta upon 2 k, delta upon 2 k minus 1, delta upon 2. So, that will be equals to, it is L naught upon 2 raised to power k plus, it is a geometric progression having k number of terms. So, it is A (1 minus r raised to power n), r is 2 raised to power k and 1 minus 2. So, that will be L naught upon 2 raised to power k plus delta upon 2 raised to power k, 2 raised to power k minus 1. It is A, okay, 1 minus r raised to power n, r is 2, okay, r is 2. So, it is 2 raised to power k upon 1 minus 2, that is this or divided with this, yeah, it is correct. Okay. So, it is L naught upon 2 n by 2 because k is n by 2 plus delta 1 minus 1 upon 2 raised to power n by 2. So, this will be the length, this will be ln. Okay. So, if you see here, so L naught ln will be L naught plus 2 raised to power n by 2 plus delta whole 1 minus 2 upon n by 2. And alpha, which is a measure of effectiveness, is ln upon L naught. So, it will be 1 upon 2 raised to power n by 2 plus delta upon L naught 1 minus 1 upon 2 raised to power n by 2. So, this is the main scheme. Let us discuss it by an example again. Okay. Now, we have to find the maximum value of the function f x, which is x into 1.5 minus x in 0 to 1. So, x L is 0 and x r is 1. So, what is the first interval of uncertainty? That is 1 minus 0, which is 1. Okay. Delta is given to us, it is 0.001, and alpha, which is the measure of effectiveness, is also given to us, it should be less than or equals to 0.2. So, we know that alpha in this expression for dichotomous search technique is given by this expression, this we have already derived, it is given by this expression. So, this must be less than or equal to 0.2. Okay. Now, if you simply delta is 0.001 and this L naught is 1 minus 0, it is 1, you simplify this. So, you will get n greater than or equals to approximately 5, but n must be even for dichotomous. So, we take n is equal to 6, that means we have to find 6 number of iterations. So, that alpha will be less than or equals to 0.2. Now, how to find the experiments? So, this we have already seen that x1 will be a plus or xl plus L naught minus delta upon 2, and x2 will be xl plus L naught plus delta by 2. So, this xl is 0 plus L naught is 1 minus delta is 0.001 upon 2, and it is again 0 plus 1 plus 0.001 upon 2. So, in this way we find x1 and x2. Then we will see the sign of fx1 and fx2, find the values of fx1 and fx2. So, we find that fx1 is less than fx2. So, therefore, the next interval of uncertainty will be x1 to xr, that is 0.4995 to 1. Okay. Again, using this interval as the new interval of uncertainty, we again find the two experiments x3 and x4 which is given by this expression, okay, because now you can take XL as this and XR as this. Again you will take the midpoint and place one experiment delta by 2 on the left side and one experiment delta 2 by 2 on the right side. Okay. You find x3 and x4. Again you see the sign fx3 and fx4, whether fx3 here fx3 is less than fx4. So, the next interval uncertainty will be 0.750372 So, in this way we will perform the next two experiments also, and finally the midpoint or the final interval will be the approximate optimal solution of the given problem. So, this is a simple iteration that how can we use such technique to find out the optimal solution using dichotomous search technique. So, thank you very much.